So I thought it'd be a fun thing to try to do some sort of like a speed test between all my different devices. And so I've written a program to run on them, and it's pretty basic for a couple of reasons. One, I'm not really much of a programmer, and I've had to learn quite a few different um, languages, even to try to enter this one program. And the other reason is I wanted it to be fairly simple so that I could adapt it to even hopefully something like this. I'm pretty sure I could um, get really like the core concept. So, I mean, this is just for fun. It's not, super scientific. So, it doesn't have to be exact, but the at least core loops of the program should be transferable to something like this, which is an old HP 15C that uses keystroke programming or something like this, which is the 32S. Um, and I've been working on it with a few different um, devices, like one of my Casios and a couple of my other calculators. And the scope of trying to test them all and go through the programs for all of them has been kind of growing rapidly. So I thought maybe for just as one video, I'd focus on, in this case, just the TI series that I have that uses the Motorola 68,000. So the 92, I have a 92 with this added expansion module to kind of make it more comparable to the 92 Plus I have up here. And then I also have a TI-89 and a Voyage or a Voyage 200, which are pretty much the same, just different form factors. And then for fun, I'm going to do the same thing on this TI-82 Stats I have, which I just really like. It's kind of a cool color scheme. It's basically almost internally identical to a TI-83 software and hardware, I think. So that's like one of the calculators I grew up using. So I'll figure I'd throw that one in for fun. And then, let's take a look at the program here and I'll kind of give you the play-by-play on it. So you can see here it starts by assigning a value to n. In this case, we're going to go to 1000. Oh, yeah. So the program, what it does is between the number 3 or from 3 to whatever n is, in this case 1000, it's going to verify and count the number of prime numbers. So, yeah, 1000 is the number we're going to. And we can see the count starts at 2, and I'll get into that in a second. So, and then I think I just got to initialize this, or the program doesn't like me for some reason. With the 92 plus, whoops. With the 92 plus and the V200 and the 89 titanium, they have internal clocks, so we can actually use this get time command to get a timestamp. So in this case, those will be where the program starts. And it'll be accurate to about a second, so probably close enough for the expected range that we're going to be working with here. I think these are all going to be pretty spread out. Then the main loop starts at the number 3, and this is the loop that'll control all the numbers that we're going to be testing in the range, so up to 1000. And I started at 3 because if you start at 2, the way the prime number verification loop works, if you start at 2, you have to add some extra little checks to it. So I figure I just skip that. Start at 3, make it easier for myself. And then it steps 2. So every other number it'll check. And so because we're starting on odds, we know we don't need to check evens. So it'll just be checking the odd values. That is about the only optimization in this program. It's just about the slowest way you can do this process. But again, it's not really about optimizing and efficiency. It's just about having something as close to identical of a program on all the different devices as I could get. So then we are into our next loop here, which starts at 2. We don't need to start at 1. This is actually to check for prime. So we know 1 is not needed. So we start at 2, and we go up to my variable here, NSQ, which is like the square of the n. So, which was done on the line above. So we take the integer value of the square root of whatever number we're testing. That's this here. Then we divide the number we're testing by our incrementing factors. And then we just take the integer value, or sorry, we subtract the integer value of that here, and then we're just stored with the remainder, so a decimal remainder. Then we test. So if that remainder is 0, then we know it's a factor, and we set the end loop value to I so that the loop doesn't continue, and then it exits out. There's a few different ways to exit out. There's like a break command or an exit command or something. That wasn't present on the TI-82 stats version of TI Basic, so I'm using this little trick that someone showed me on Calcverse to exit for loops. Once the loop is over, we know that there's only 2 ways for it to end, which is either it exits on a factor where there's 0 remainder, or it completes the loop and exits with a remainder. So if there's still a remainder, we know it's gone through the full loop and not found any other factors. So then we can add 1 to the count for the prime numbers. So and then once all that's done, we get a timestamp for the end, and we display it all. So we can show the count, the start time, the stop time, and then it's over. Oh, I can't remember if I said, but the other thing is, the reason why we're starting with the count of 2 is because we're starting with the number 3, not the number 2, so we have to add 1 to the count. The other thing is, if you look, by starting at 3, this NSQ value will, the integer value of the square root of j starting at 3 will be 1. And then when it goes into this loop, the range would then technically be 2 to 1 with a step value of 1. So we're already outside the range of this loop, so it just bounces off when testing the number 3. And so that's the other reason why we need to start with the number 2. So 1 is for skipping the number 2, 1 is for the first loop doesn't actually activate because the range that I've set. So that's the program here. And I'll quickly just show the same version on, or a comparable version on the the 82 here. So same thing. So we're going to be testing to 1000. The count is 2. On these calculators, so as I went on, the more I was doing it, I just simplified the variables because I got tired of typing them in, especially on these alpha shift keyboards. They can be pretty annoying to me, and when I'm using 3 or 4 different formats of them over the course of a weekend, it's really hard to find the letters, which, by the way, this one I found super annoying. If you look here, we get Q, R, S, U, V. So the Y, Z, and T are dedicated variable buttons you can use, I guess. So they're broken out up here, but that means like when you're typing words or variable names that have T in it, and you're like used to hitting the alpha shift, you have to actually shift out of the alpha mode to put the T in. So that's super annoying. I found on this thing. I just had to gripe about that for a second. But yeah, I'll just quickly go through. You can see it's essentially the same program, just different variable names. And then the formatting is slightly different, right? We don't have endif and end4. We just have ends. That gets a little tricky to keep track of because especially you don't actually indent or anything in this version. And yeah, there you go. That's the whole program. So what I figure I'll do is I'll go around and I'll just start them up. And like I said, the V200, the 92 plus up here, and the 89 will have timestamps within them accurate to a second. That'll be good enough for this, I think. And then these 3, what I'll have to do is just review the video after to figure out exactly ish how long they took. And yeah, what I'm thinking is maybe I'll run it 2 or 3 times to see, if there's any wildly different results, but I kind of think they'll all be more or less the same each time. So yeah, I'll just get them all started up here. And we gotta do, yeah, and then probably start with this one because it'll probably take the longest. So there we go. And it's kind of unnecessary on these ones since they're gonna have timestamps, but yeah, I suspect this will take about 3 or 4 minutes to complete, and then we'll check back with the results after. Okay, so I'm back and I've written down all the times for the 3 runs I did, and maybe what I'll do is I'll just put the footage of those at the end, so you can just see for yourself or whatever. I'm not sure it'll be terribly interesting, but some pretty surprising results, I'd say. So I'm not sure how good this is as a test. If I would have had to guess up front, I would have probably said the V200 and the 89 Ti would be like first and second. I'm not really sure which are which, but those are just because those are the newest. Then I would have said 92 plus because that's the one just before those two. I would have gone for the 92 pseudo plus or whatever. So what this is it's just a regular TI 92, but it has an expansion module in it to kind of make it comparable to this. So I would have said that's maybe like fourth place behind, those three. Then I would have said this, and I would have put this last, just because that's basically the order of manufacturing and design. Really, I would have just said the newest ones are the fastest, the oldest ones are the slowest, and it would just go in that order. Um, the three here, I guess I forgot to go into this earlier, but this one, and this one, they were on the same chip as these two, um, but I think they're clocked at 12 megahertz, whereas these two would be clocked at 10 megahertz. And then this has whatever the expansion pack does. And then this one is a Z80, a Zilog Z80, I think, maybe. But it's clocked at, I think, 6 megahertz. So, um, but yeah, so I say that because it's kind of a surprising result on this. I wrote down the times here, and because I'm using the internal timestamps, so like you can see here, this is kind of goofy. It goes from 59:57 to 2:37, but those are in actual like clock minutes. Whereas the 82 stats, I was just writing down um, the times off the video. So, um, so more importantly, it's over here. So you can see nothing was different by more than 1 or 2 seconds on the three runs. I think the 92 with the module, lowest 23, highest 25. Again, just accurate to the second, but you can see there's not much deviation. And then, yeah, based on that, so the V200 and the 89 Ti are basically tied at, 2 minutes and 40 seconds. Surprisingly, then, the 82 stats was the next fastest up here with about 3 minutes and 10 seconds, maybe 3 minutes 11 seconds. Then the 92, this is kind of upsetting. The 92 with the expansion pack was the third fastest. What is that? About 3 minutes and 24 seconds average. And that's upsetting because actually I like the TI 92 Plus is my favorite of these right now. Really like using that one. Maybe I should switch back to the expansion pack version, except the screen is brutal on those. Yeah, so 92 Plus was the fourth or fifth, however you want to say it. So that's about 3 minutes and 39 seconds. And then 92 was last, about 4 minutes and 44 seconds. So yeah, a bit of a weird result, a bit of an unexpected result. I wouldn't have guessed that at all. Like I said, I would have just gone by, you know, oldest, slowest, newest, fastest, and called it a day there. But yeah, pretty interesting. I'll try to put the code for at least these TIs into the description or something, so you could try to write it yourself onto whatever calculator you have or something comparable to see what it comes up like. But anyway, yeah, thank you for watching, and hopefully in the future I'll be able to test some of my other devices and see how they compare. So there we go. Okay, so I just want to angle these up to get the timestamps on camera a bit better. And then, yeah, we'll do another round. So here we'll do round 2. And once again, there's that one. And Okay. And once again, let's get the timestamps off these for round 2. We'll have to use the video to check the rest, and we'll do one more. Okay, we're going to do one more run. So here we go, the 82, third run. It's going. And then over here, that's not how you do that. It's the enter button. Then that one. And Okay, let's get the timestamps up. Once again, so they're kind of hard to see. And that was third run.